Hello everybody. Continuing on our lecture series of EC206 Computer Organization Module 6. In this lecture, we will be studying associative caches. Remember, we had studied that caches are organized into three types based on the number of blocks in a set: direct map caches, n-way set associative, and fully associative caches. We will be studying the two associative caches in this lecture. The first is the n-way set associative cache, which has got n blocks in a particular set. So the number of set becomes b, the number of blocks divided by n, the number of blocks in each set. And fully associative caches have only one set, so it contains all the b blocks in that one set. Remember, in part 2 of the lecture series on caches, we had studied the direct map caches. Just a recall of how the mapping is done. We had studied an example of an 8-word cache and seen how the various memory addresses, main memory addresses, are mapped onto this one cache. Now, a cache conflict occurs when multiple memory addresses map to a single set. When a set already has data from another main memory location, then we say that a conflict has occurred. Now look at this particular set, that is set 1. Now suppose the first processor memory access has brought in this data word into this particular set. Now the next processor memory access probably requires not this data word, but it may require, let us say, for example, this data word. Now when it brings in, it has to bring it into the same set. So this set is already occupied by this. So now this data, the first data, has to be overwritten, and then the next data will come in and sit there. So this is what is called a cache conflict. What we had already brought earlier is now gone, and now the processor brings in this data. Now what happens if the processor wants this data in the next instruction? It will have to go access the main memory once again and bring it here, increasing the memory access time. And this is called cache conflict. Now the hardware of the direct map cache we had seen earlier, we have seen that there was hardware required to match the tags in the main memory address and the tags stored in the cache. Only when the hit value was equal to 1, we could take the data. Now let us look at n-way set associative caches, also called multi-way set associative caches. These type of caches try to reduce cache conflicts. What they do is, instead of having only one block in each set, they provide n blocks in each set. So suppose one data word maps to, like we had seen in the previous example, to set 1. And in the next read cycle, another data word maps to the same set 1. In direct map cache, we had a cache conflict and the data had to be overwritten. Now if we have, let us say, 2 blocks in the set, now there is place for 2 data words to come into each set. So by providing n blocks in each set, we can reduce cache conflict. Each memory address still maps to a specific set. But inside the set, since there are several blocks, it can map to any one of the n blocks in the set and thereby reducing the cache conflict. Okay. So a direct map cache can be called a one-way set associative cache where n is equal to 1. Now, the number of blocks in a set n can also be called the degree of associativity of the cache. Now, let us look in detail at the n-way set associative cache using a particular example. So, we know that there are n blocks in the set and the number of sets S is equal to B by n. The number of blocks B is given by the formula C by B, where C is the cache capacity and B is the block size. So, as an example, consider a cache that again can store 8 data words. Capacity C is equal to 8 data words. Let us take the example that n is equal to 2. Since n is equal to 2, we call it a two-way set associative cache. Now, what is n is equal to 2? It means there are 2 blocks in each set, or we say there are 2 ways. So, then there are 2 blocks in each set, there are 2 ways. When there are 4 blocks in each set, we say there are 4 ways. Okay. So, now let us look at the diagram. So, now the number of sets has reduced. What is the number of sets? Number of sets is B, the number of blocks divided by n. So, what is B? B is cache capacity C divided by B. Cache capacity is 8, and let us assume that there is only one data word in each block. So, the block size B is equal to 1. So, capital letter B, that is the number of blocks, is 8. So now since there are two ways or two blocks in each set, we say S is equal to B by N, that is 8 by 2, that is 4 sets. So in the direct map cache, we had seen 8 sets, but here now we are seeing only 4 sets, set 0 to set 3. But we are seeing there are two data words or two blocks in each of the sets. Earlier we had only one data word that could be stored in each set, and there were 8 sets. Now we have 4 sets, and in each set you can store two data words, or you have two blocks. So 4 into 2 is again 8. Capacity is the same, but the arrangement is different. So for each data word, we had seen in the direct map cache that we have to have a tag and we have to have a valid bit. So for each block or for each way, we have their own separate data words storage areas, that is 32 bits, and then you have the tag bits, and then we have the valid bit. So this is called way 0 and this is called way 1. Now this is the main memory address that is coming. So, or the memory address that is coming, the processor wants to access data. So what happens is it first looks in the cache according to memory hierarchy. So when it looks into the cache, we know that the LSB2 bits are 0, 0 for word alignment. Now the number of set bits is now equal to 2. In the direct map cache for the same capacity, 8 words, we had number of set bits was log 8 to the base 2, that was 3. Now we have log 4 to the base 2, that is 2. Now why 4? Because the number of sets is equal to 4. So we need only 2 bits for the set bits. The remaining 32 minus 2 minus 2, that is 28 bits becomes the tag. So how did tag become 28? Previously tag was 27. Now the number of set bits has reduced to 1. So one more of the bits becomes the tag. So what happens here is that we have more hardware that is required for the comparison. So when one memory address comes and a set is selected, this is 0, 0, 0, 1, 0, 1, 0 and 1, 1. Let us say, for example, we got 1, 0 over here. So this set is selected. Okay. In this set, there are two blocks or two ways. So which of these ways is going to go with the data from which way are we going to use? Or can we use at all any of the data? Is the data is what we require. How the comparison is done is just like we saw in direct map cache. Each of the tags, look at the tag here from way 1 is compared to the tag from the memory address. The tag from way 0 is also compared to the tag from the memory address. So you have two equality comparators instead of one, and one of them only will give an output 1 if at all it is going to give an output 1. So if the required data is there in the cache, only one of these locations it is going to have the data. Only one of these equality comparators will become 1. Maybe if the data is not there in the cache, then both the equality comparators can become 0. Both cannot become 1 anyway. Okay. So valid bit is also checked for each case, just like in the previous direct map cache. So if there is the required data in way 1, then hit 1 will become 1. If the required data is in way 0, then hit 0 will become 1. As we know, hit 1 and hit 0 both simultaneously cannot become 1. They can be 0, 0, they can be 0, 1, they can be 1, 0, but they cannot be both 1, 1. So here you have an OR gate. If either hit 1 or hit 0 is equal to 1, then hit will become 1. Okay. So if the tag matches in way 0, then hit 0 is equal to 1. If the valid bit is 1, if the tag matches in way 1, then hit 1 is equal to 1. If valid bit is equal to 1. Okay. Now, if one of these things hits, then hit will become equal to 1. If hit is equal to 1, data from the cache can be used. But which data? Is it this data from way 1 or this data from way 0? For that, we require the use of a multiplexer. So the multiplexer selects one of these two data based on the hit 1. If hit 1 is equal to 0, then way 0 data is given out. And if hit 1 is equal to 1, correctly, then way 1 data will come out. So if hit is equal to 1, then the corresponding data can be used. If hit is equal to 0, then the cache misses and the data has to be fetched from the main memory. So an n-way set associative cache has got lower miss rates than the direct map cache because of fewer conflicts. There's more number of blocks in each set, so cache conflict reduces, so lower miss rates. But they require additional circuitry. You saw that the number of equality comparators, then the AND gates and the OR gate, all that increases as n increases. So they are slower and more expensive to build. Also, suppose both the ways, in the previous example, both the ways are full, then which way should we replace? Should we replace way 0 or way 1? That question has now got to be answered. But most commercial systems use set associative caches because of the lower miss rates because of fewer cache conflicts. Now, in a fully associative cache, we know that all the blocks are in the single set. There's only one set in a fully associative cache, so all the blocks are in the single set. So you are seeing here the same example, cache capacity C is equal to 8 words, the block size B is equal to 1. Okay, number of data words in each block is equal to 1. So B is equal to C by B, 8 by 1, which is equal to 8, and S is equal to 1. So this is one set. Okay, and number of ways n is equal to b, which is equal to a. So you have 8 ways, way 0, way 1, etc. up to way 7. Each of them have their own tag, data and valid bit. See, tag, data and valid bit. Okay, so this means that you need 8 sets of equality comparators and AND gates and an 8 input OR gate for the final hardware comparison with to take the, and then you have to have an 8:1 multiplexer. Those things are not shown in this diagram. Okay, so when the processor requests for data, 8 tag comparisons must be made because the data may be in any one of the 8 blocks. It may be or may not be, but it may be in any one of the 8 blocks. So 8 tag comparisons have to be made. And then an 8:1 multiplexer chooses data from one of the 8 ways, and that data is used if the cache hits. As I said in the previous slide, the comparators and multiplexers are not shown in the diagram because they're really huge number of comparators and multiplexer and then the size of multiplexer. Okay, but we can see that because it is fully associative, it has a fewest conflict misses. Cache conflict is the lowest. Okay, but the disadvantage is that it requires additional hardware and is best suited for relatively small caches. So as a summary of cache organization, the number of ways in a direct map cache is 1. The number of sets is B. In a set associative or n-way set associative cache, we have n which is greater than this 1, but it is less than this B. Okay, and the number of sets is B by n. And in a fully associative cache, the number of ways is B and the number of sets is 1. By increasing n, we can reduce miss rate by reducing the number of cache conflicts, but we know that it requires more hardware. You can also do one thing. You can reduce or you can increase B. This takes advantage of the spatial locality to reduce the miss rate. Usage of spatial locality means when you're bringing in one data word that the processor requires, you bring in a few more data words that are next to that particular data word. That is taking advantage of spatial locality. We are saying that if the processor wants a particular data word right now, it might require the next few data words also. So if I increase the block size B, I can take advantage of spatial locality to reduce miss rate. But increasing B reduces the number of sets, which will again increase cache conflicts and thereby increase the miss rate.